We discussed previously the example of the one person who did not receive the participation awards and whether or not that affected her overall stress level. We found that she had a stress level of 18. We compared it to the population and we were not able to reject the null hypothesis because her 18 fell within the total normal random sampling from that population. We didn't find that she was some sort of an outlier that we would think comes from a different population, i.e. that not receiving participation awards would develop in her resilience and make her more resistant to that type of stress. Now what we're going to do is take apart why that's a problem. You know, we only tested one person. We only gave one person that one individual the treatment. We only gave one person the treatment and we compared her to everyone else who gets the participation awards. That's a really poor design for a study, and here's why. Let's say that there's a real effect of the independent variable, whether or not somebody gets in a participation award, on their later stress level. We may have missed it. We may have made a type 2 error. If you remember the type 2 error that we just discussed, is where you don't find, based on your research, based on your decision, an effect of the independent variable, but in reality there is one. One of the critiques of our study could be you only did one person, and perhaps that person's lowered stress level was immense from the fact that she did not receive participation awards and she learned to develop resilience in the face of stress. So she doesn't experience anxiety the same way that the rest of us do, who all got the pat on our butts for just showing up. She really only got rewarded for sticking through the tough stuff and developing a sense of individual competence and resilience in the face of failure. But we didn't notice that because we only tested one person. Now what we're going to do is we're going to test groups of people and find the mean of their sample and say, well, this is the average that the people that got that particular treatment experienced. And we'll ask the question of, is that a likely scenario that we sample from the population that did not receive that treatment and that we get that same outcome as their mean? This is called testing with means of samples. And this will be Chapter 5, Testing with Means of Samples, and your introduction to a t-test with means of z-test with means of samples. One of the issues that we have is oftentimes we'll take our anecdotal evidence and we'll compare that to the group. And we'll say, well, I had this experience, therefore this is real for everybody. And we can't do that. Too often we see that happening in the media these days where they'll give you a story about a single person that something terrible happened to, and then you assume that that's happening to everybody at the same rate. This is not true. What we need to do is to rely on data about groups to teach us about what we could expect for individuals within that group. To take an individual and then to ascribe to them everything that their population believes or acts like is just stereotypical and prejudiced. What we really need to do is to take that population average and then predict for us how likely we are to see that outcome in a particular individual. Don't think that this is not something that is a natural habit for people to do. We do it all the time. We make anecdotal evidence our truth, our lived experience. And that, my friends, is a road to perdition you do not want to travel down. You want to rely on statistics about populations because, as we'll find out, there's far, far more variability within a group than between groups. Imagine I got permission from one of the administrators who was in charge at Los Rios to run an in-person class. And I could randomly assign you to either an in-person class or an online class. If I could do that, I'd be able to run an experiment and see if online instruction is different than face-to-face instruction. You know, I'd meet with one group of you for 16 weeks, twice a week for an hour and a half, and we'd have office hours, and there'd be a normal every regular semester stats class. The other group would be randomly assigned into an online class where you'd be watching this lecture. What's your hypothesis about the grades at the end of the semester? What do you think the class averages would be? Now, I know my class average. So the class average that I get is, you see that? Mu is equal to 74. That's the class average that I get normally. So face-to-face, because I've never taught this class online. The standard deviation is a little high. So the standard deviation for this is 8. One of the questions we could ask is, does teaching online lower class scores? The question remains, does teaching online change student scores from when we took face-to-face classes? We have a population that I know about, all of my former students. This is the average and the standard deviation for that group. The question we could ask as researchers is, does online teaching lower test scores so that the class's average will be lower? Now, interestingly, there's 35 of you. So I'm guessing some of you, and you're in my online class obviously, some of you are going to be good at stats. You've prepared, you're confident, you work hard, you're going to be good naturally. Some of you aren't so good. There's going to be variability in your class. That's normal. I expect that. And there's variability here, right? So there's this, and then there's that as the average distance. So 74 plus 8, if you go 8 more than 72, you find out that's an 82. That's pretty good. That's within one standard deviation of the mean. So that's normal. Now, the question is, how much would we have to get lower as an online group to suggest that statistically significantly we are different from the face-to-face class averages? I don't know. But if we use the 6 steps of hypothesis testing and some made-up data, I make it up, we can figure this out. Step 1, if you remember it, it is restate the question as a research hypothesis and a null hypothesis about the populations. So 1, we have 2 populations, right? Population 1 is just online psych 330 students. Studs. Pop 2, that's just students in general. Students in general who took Psych 330. The HO that I have is that these two are not different, right? So the HO, population 1, online students taking Psych 330, is equal to population 2, that is students who took the face-to-face version of this class. That's our potential, right? This is what we have to start with, and we determine the probability that this is true because we actually think, I think, that the research hypothesis or the alternative A hypothesis is that population number 1 is going to be less good at this class than population number 2. Before you get all mad at me, I'm making this stuff up, so don't freak out that I'm saying that my hypothesis is you'll do worse than they do. Just relax. We'll see what happens.
These 2 do not work.
Okay, I'll take them. All right, Henry here. I've asked to come in for our second step of hypothesis testing, which is to determine the characteristics of our comparison distribution. Now, if you remember, I told you that I already know what students who take Psych 330, what their scores are like in face-to-face classes. That's our comparison population, who we're going to compare you to. Not you two like Bono, but you, who we're going to compare you against is going to be the class, all the classes that I've taught for the last, 11 years here at CRC. So we know what their mean is. The mean, as we use this Greek letter mu to denote a population. That's the population of all my students thus far who have all been taught face-to-face. They had a mean class average of 74. And we know that the standard deviation, or this is the Greek letter sigma that represents a population's standard deviation, is 8. So, we've completed step 2. Now, what might be helpful to do is to draw out a normal curve that has a mean of 74 and a standard deviation of 8. What's 74 minus 8, son?
74 minus 8 is 66.
Thanks. 66, he says. And what's 66 minus 8?
66 minus 8 is 58.
All right, so he's got that down. Okay, we've drawn out a distribution.
You need it.
I need to try what?
Tastes so good.
What is it?
Pretzel with Nutella.
It's a pretzel with Nutella. Nutella?
Yes.
That's good. Jonah, you want to say hi to the class?
Hi.
You say hi?
Hi.
All right. I'm doing some work here. Okay.
Oh my, I just got...
Don't worry, it's dry erase marker. You can get it off your body. Okay. This is the distribution that has all the students that I've had before. Now, you're a new class. This is an experiment that's brand new. We're going to compare you and your average, and we'll say, well, where does the group of you fit in here? Now, if you guys fit in somewhere down here, we're going to say, you guys are doing pretty good. If you fit in down here, we're going to say, you're not doing so well. And we'll attribute that to, because I'm still me, I've been me for the whole time I've been doing this, we're going to attribute that to the method of delivery, so online versus face-to-face. But there's a problem. This is a population of individuals. All the students who have taken my class before, that's their average score, and that's the standard deviation for their group. The problem that this is that there's 35 of you. And so what we're going to need to do is to create what's called a comparison distribution that is reflective of groups of 35, not groups of 1. This is all the students, all one individual, all mashed together for the population. This is not what the population's distribution would look like if it was for, hey Henry, what did you draw?
A computer.
Oh, a computer. That's what you guys are all taking this class on, probably a laptop, huh? Okay. Thank you, Henry.
Okay.
We can't compare groups of 35 of you and the average class score that you guys have, the mean for our class. We can't compare that to groups of individuals. What we're going to have to do is create what's called a sampling distribution. And the sampling distribution is basically, I'm going to take all possible combinations of 35 students out of this group of individuals. I'm going to take all possible groups of 35, right? There will be one of them that's the lowest 35, one of them that's the top 35. There will be one of them that's 34 of the bottom and one of the top. And one will be 34 of the top and one of the bottom. One will be 33 of the top and 2 of the bottom. And one will be 33 of the bottom, 2 of the top. You get what I'm saying? It will be every possible combination of 35 randomly sampled, again, randomly sampled from this population. That will create a comparison distribution that is a distribution of means. Okay, what do I mean by that? Let's say I start throwing random, boom, boom, boom. I just start throwing random darts at this, and I pick scores that are wherever those random marks are. If I do that, and I do it 35 times, I'll take those scores, I'll add them up, divide by 35, and get the average for one group of randomly selected scores in this distribution. Now, obviously, we use a mathematical model in a computer to do this because it takes too long, but we can use the principle that we understand to create a sampling distribution and to create something called the distribution of means. So that's what will be next in our class, is the distribution of means. All right, scary equation. There was some weird person standing behind my car, so that's why I had to move away. Sorry, we're back here with the scary equation. The scary equation is just variance. You know how to calculate variance. It's just standard deviation times itself. We divide that by n and we take its square root. When we do that, it gives us the average amount groups of that size differ from the mean, the distribution of means mean. So this is a simple way to calculate it, but here's the concept behind it. The more we randomly sample from a population, the more we're going to have an accurate picture of that population. The less we randomly sample, there's the chance that we select somebody out in the outskirts, right, way out in the tails, and that's not representative of the group. What we do here is we're representing the larger our n size is, the smaller the smaller variation there should be in groups' means away from the mean of the group. This seems very complicated, but let's look at it. Okay. Turns out that strange person hiding behind my car was just there for a surprise party with some neighbor. Although I don't think we're supposed to have surprise parties. I don't think we're supposed to have a bunch of random people at our house. Anyway, you do you. We'll do us here. Okay. For our group, we knew that we had a standard deviation of 8. So the variance for that group, variance is just square of standard deviation. So what's 8 times 8? 64. Okay, we know that we have a standard deviation of 8. Our variance is 64. This is for the population of individuals. That's face-to-face students. To get what it would be in a distribution of means, we're going to take this and we're going to divide it by n. The n for our group we said is 35. So now I'm going to need my handy dandy calculator. Okay Google, what's 64 divided by 35?
The answer is approximately 1.828571.
1.828571. $42857. I could keep writing, waste our time. Now what I need to do is take the square root of that. Okay? Gotta get rid of this little thing. If we want to get to standard deviation for distributions of means, I take the square root of that. Okay, let's see if I can do this. I don't know how to do these things. Okay, 1.8258571428. It doesn't matter. We're going to take its square root. Apparently I have to do that before. I wish I had my old calculator in front of me. Okay, the square root of 1.828. We're going to do the square root of 1.28. Okay? That equals 1.53. That's all we're going to get. 1.53. So here, we know that each group of 35 students on average differs a standard deviation of 1.53. So, if we took all possible groups of 35, we would find that 68% of them are within 1.35 of that population mean that we said was 74. So the question is going to be, what do we find with you, the online class? Are you within a couple standard deviations, or are you way out in the distance? We don't know yet. We're going to find out, and I'll tell you in a bit when I make up the numbers. So we know a couple things already. Okay, we know that the comparison population has a mean of 74. We know that they have a standard deviation of 8. And we also know that for our group, which has an n of 35, we're going to figure out how much we expect groups like this to differ from the mean of their group, we found that the mu for the distribution of means is the same thing. And we calculated how much we expect groups of 35 to differ from that mean based on this and this. We found that that standard deviation for the distribution of means was 1.35. So instead of differing on average by 8, that's what individuals in the population differ by, right? So any individual student who took my class, they differ by 8 from that. But when I talk about an entire group, all 35 of them, they differ by 1.35. So that is saying something significant. We've gone from a distribution that looked like this, 74, 82, right, 90. What did he say? 66, 58. That's what the group of individuals looks like, right? That population looks normal. Our population now is going to look drastically different because instead of differing by 8, we only differ by 1.35. So 1.35 less than 74, not very good at math. I could probably do this in my head, but we're going to do it here. All right, 74 minus 1.35 is 72.65. So again, this is for groups of 35. I can do one more than that. So that would be 74 plus 1.35 would be 75.1 or 0.35. One more than that would be 76.6 or 70. One less than that would be 71.3. So here we go. We've got our distribution that we're going to compare our group of 35 to, because this is the comparison distribution that takes into account what it would be like for groups of 35 to be pulled from that population, the population of all my former students. Now we know what we can compare our group to. We've calculated the distance that we expect groups of 35 to differ from that mean, and it turns out that it's much smaller than the population of individuals. So we're going to ignore this now, because we're not comparing one person. Remember, we compared that one person, and even though she had lower anxiety than the rest of the group, we weren't able to reject the null because it was just silliness. You know, she had an 18, but she would have had to have really, really low to have less anxiety, given that we were comparing her to a population of individuals. Now we've got 35 of you, 35 students, and so this is what we expect if there's no difference between you and all of my previous classes. So we have our comparison distribution. We're on to step 3. We've determined the characteristics of our comparison distribution in step 2, and we found that we think that groups of 35 will differ on average by 1.35 from the mean of 74. Step 3 is to determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. How we're going to do that is we're going to use what the principles that we learned from the last portion, the class about percent under normal curve, and we're going to consider our comparison distribution and find where are we comfortable with rejecting the null hypothesis. Two things that we need to figure out. One is this a one-tail or a two-tail test? What do I mean by one or two-tail test? A one-tail test is one where we're saying we think something's lowering or raising or making worse or making better. Those statements where I have a directional hypothesis is a one-tail test. I'm only looking in one tail of that distribution. But a two-tail test is one where I say, I wonder if there's a difference, or I wonder if there's a change. I wonder if there's a significant alteration, right? Those are the words that could be, an alteration could be better or worse. A change could be for the better or for the worse. So a two-tailed test is when we don't know which direction we're hypothesizing. We're just thinking this is going to be different. In our case, I've already said I think online learning is going to have lower test scores. I shouldn't be giving this example because of something called stereotype threat, but I'll teach you about that later. Please don't think this is all made up. I'm making all this up just to teach you how to do this. So it's not really about you. It's just you're a convenient example, right? Online class I've never had before. It's a natural experiment with all the previous classes I've taught face-to-face. Please, I'm not thinking you're gonna fail. I hope you do well. I hope this is wonderful. I hope this changes everybody and we all get better. So, we think that this is a one-tail test. One-tail test. Now, it's a one-tail test because I think that online classes are going to do worse than the face-to-face classes. That's my hypothesis. Should I have that hypothesis? Probably not. Why? There's not enough data out there to say one way or the other, and if you don't know, you should take the perspective of maybe it makes it better. I'll look in both tails. And we'll get to that in a bit. I'll teach you how to do a two-tail test later. We'll give an example of that. Currently, we're just sticking with this one. This is a one-tail test because I said I think online is going to make scores go lower from the comparison population. I could have said I think they're going to make them go higher, and we wouldn't be in the same situation that I'd have to coax you back from all of your disheartened woebegones. It's a one-tail test. The next thing we have to figure out for step 3 is whether or not we want to have a very stringent alpha level or we want to have a normal alpha level. The normal alpha level that people choose in the social sciences, this is a social science thing, this is an education thing, is 0.05. And we say if we find that our group is so extreme that it happens less than 5% of the time in our comparison population, we're going to reject the null and we're going to say, yep, there is a difference there. In our case, it would be that there would be a lowering of test scores from face-to-face classes via online. That's what we're going to say. But you may choose a 0.01 alpha level. I don't care. It's completely up to you. Choosing an alpha level just says how likely or how comfortable are you being wrong when you make a statement or a claim about this in the future. So if I say online classes are bad and I could be wrong 5% of the time, I might not be so cavalier about making that statement. But if I do a 0.01 alpha level and I really found that online classes at a 0.01 level, I'm only wrong 1% of the time, I could be pretty confident claiming what I've found and being assured that there's only a 1% chance that I'm incorrect about that claim. I'm going to go with the 0.05 one here because when in doubt, go with 0.05. Alpha level, 0.05. So everybody can see this? We've got a one-tail test, 0.05 alpha level. The question is, well, what's the cutoff? What's the cutoff here? In our comparison distribution, you remember our comparison distribution, right? We had a mean of 74, and what's the standard deviation? Remember, our comparison distribution is for groups of 35, so this is the one with the small variability, right? The standard deviation for a distribution of means is only 1.35. So 1.35 is going to be 75.35 and 76.3 and 72.65 and 71.3. Now, we have to figure out where on this curve is that low 5%, the lowest 5%. So where is it that if I was blindfolded and I threw a dart, I would only hit 5% of the time? And it turns out it's here on the lower end. Where we figured that out? You turn to your back of your book. So let's get the books. We'll find where does this table say the percent in tail is 5%. We go here, and we find that it says 5% in tail. It doesn't actually say 5% in tail. It says 5.05 and 4.95. So there's two z-scores here. One's a 1.64 and one's a 1.65. Either of those are sufficient for you to deal with it. Sorry, got the kids going through the backyard with all the boats. All right, I'll hold on first. If we get started back on our project, what we are attempting to do is to find out if the online class is a different group of people in terms of their outcomes for their scores than the courses students who have been taking my class over the last bunch of years, more than a decade. Now, what we did is we went through the first 3 steps of hypothesis testing, that is to restate the question as a research hypothesis and a null hypothesis about the populations. That is to determine the characteristics of the comparison distribution. That's where we had to manipulate the individual population into a population of groups of the size of your class, 35 students. And to come up with a new comparison population statistics, that is the mu for the distribution of means and the standard deviation for the distribution of means. When we did that, we found a new comparison distribution that had a narrower range of variability. Now, we finally went on to figuring out where the cutoff will be for us, that if we find out that this class, this online class's scores are below that score, then we're going to reject the null hypothesis that online is not different from face-to-face, and that will suggest, and we will claim with confidence, at least 95% confidence, that there's a difference in online being lower scores than normal face-to-face Psych 330 classes. So that's where we are right now. And my phone started ringing. Let's see who this is. Potential spam. Hello? 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 No one's there. Oh, it's from Florida. Hello, Florida. Not from Florida. Okay, where were we? Sorry for that interruption, but this makes online class feel so much more like it's real. Okay, when we look at step 4 is to determine your sample score on the comparison distribution. So we have to write out our comparison distribution here. And our comparison distribution, oh, by the way, the mean of your class at the end of this, the mean score was a 70.31. I'm telling you the future. That's what it'll be. Okay. Problem is, we need to figure out where on a comparison distribution that score is. The mean for your group, you had an N of 35, right? 35 of you. When I averaged all your scores at the end of the semester, this is future Professor Frizzy talking to you. We're going to compare you to the known population. The known population has a mean of 74, and groups of 35 from it differ on average 1.35. So that's 75.35, 76.70, that's 72.65, and 71.3. This is our comparison population. That's what your score was, so now we need to put that score on this population. But first, we want to look at where our area for rejection of the null hypothesis is. 71.786. That is our cutoff. So if our score is in this area, this darkened area here, so I darkened up that area, that is the critical area for rejection of the null hypothesis. If anytime we create a comparison distribution and then we do this either in a one-tail test, just like this one is, because I said I think online will be lower, or in a two-tail test where there's both a critical area for rejection of the null hypothesis in the higher end of the curve and in the lower end, if your sample score, this is again step 4, determine your sample score on the comparison distribution, we need to take your sample score, this is the score for our sample, 70.31, and we need to put it on this distribution. Now where would 70.31 go? We got 74, 72, 71, so 70.31 would be like right here. So is that in the critical area for rejection of the null hypothesis? Well, it certainly isn't here. This area represents normal distribution of stats classes grades, final grades from Professor Frazee. And that's what we would normally suggest happens 95% of the time above this line, is that's where groups of 35 will have scores in that range. Online classes down here. What does that mean? We're going to move on from step 4 to step 5. So step 5. So the way to remember these steps is step 1 is to restate, and then there's 3 decides, or I'm sorry, there's 3 determines, and then there's a decide. So restate, determine, 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 decide. So this last step in the book is decide. My last step is explain. So decide whether to reject the null hypothesis. What's the null hypothesis? In our case, it is that the group taking an online class will be no different. There's no difference. That's what the null hypothesis states. No difference between the group that's taking normal face-to-face classes and that group that's taking it online. That's the null hypothesis. Now, if our score here placed anywhere in this part of the curve that's open, we would have said there's no difference between them and our normal classes. But because we found that our score for this sample of online class has a very low score compared to the rest of all those groups of 35 from all of my other classes that have been face-to-face, because it's so low, we wouldn't expect randomly to get a sample like that if there was no difference between online and face-to-face. This happens less than 5% of the time that we take groups of 35 from all of my students in the past. So this is very rare. It's like, say, seeing someone flip a coin 10 times in a row and it's heads. It's like, say, playing blackjack with somebody or Texas Hold'em with somebody and they get 4 aces. It's too rare to be a coincidence. This isn't chance acting alone. This represents, hey, there's a difference in online education. It's not as good as that face-to-face education. I've made up all of this. I hope you all do well. I hope we figure out the new way to teach everyone. But in this instance, step 5 is decide whether to reject the null hypothesis. Oh, we're rejecting. We're rejecting for sure. So we reject the null hypothesis because in step 4, when we determine our sample score on the comparison distribution, it's in the area for rejection of the null hypothesis. That's what this shaded area is called. So we reject HO. That's step 5. Now the last step is the toughest one. This is all math. The last step is to take math and without saying sample score or comparison distribution or standard error of the mean. I just told, that's a new one for you. That just means standard deviation for distribution of means. Same thing. Again, multiple words, super confusing. Rejecting null hypothesis. Like, what is this? We have to take all of this work that we did and we have to make it accessible to everybody. So, what do? We need to tell them that taking online classes tends to have worse scores than if you take face-to-face classes for Psych 330. Now, we don't say that for all online classes, right? Because all we've done is studied my Psych 330 classes. We can't make a giant big statement saying all online's bad. Maybe I'm a bad online teacher. That still remains to be seen. But you can at least make the claim here that the Psych 330 online students did worse than we would expect, right? This is something that we would not expect. So we're going to tell students it is likely that groups who are online taking Professor Frazee's Psych 330 class will do worse than the groups who took his face-to-face Psych 330 class. That's the best we can do. Just say, simply put, what do you tell an 8th grader? Online classes get worse grades. That works for step 6. So now we've gone through step 1, restate the question as a research hypothesis and a null hypothesis about the populations. Step 2, determine the characteristics of the comparison distribution. Step 3, determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. Step 4, determine your sample score on the comparison distribution. Step 5, decide whether to reject the null hypothesis. Step 6, explain it to an 8th grader. Taking an online class gets worse grades. Welcome to hypothesis testing with means of samples. Good morning, class. Jonah just woke up and I figured we should do some morning math time. What do you think, buddy? You don't know? Okay, we're going to start off with the easy one. This is called a
Triceratops.
Triceratops. Why do you think it's called a Triceratops?
Don't know.
Do you know what tri means?
I know what a type of means. Like you try working on stuff.
What about a triangle? What does a triangle mean?
I don't know.
What is a triangle?
Something that has 3 corners and 2
Oh,
points.
so a Triceratops might be something that has
3 triangles.
3 triangles, not 3 triangles. What does a Triceratops have?
3 horns on the bump.
Boom! Triceratops has 3 horns. Math class with Jonah.